So, thank you everyone for coming to this little award ceremony for the Mechanistic Interpretability Hackathon. And this is great. It's been a couple days since we ended, and it's been amazing to see all of the freaking awesome projects. So we've had 15 amazing submissions, and actually a bit fewer submissions than the last Interpretability Hackathon, but I think personally that the quality of these submissions are amazing, and it's really, really rock and roll to see all the different ideas people have come up with. So there's it also seems like there's a great energy and a bunch of direction from this, and it provides sort of a bright future for AI safety. But let's jump directly into the prizes. So on a fourth place, we have soft prompts are a convex set, and this is from the Mental Leap team from Israel. And this is super interesting work, and we also have Itai Yona, who is helping, or who will explain and present some of their work a bit later. So I'll jump a bit over what it's about, but it's amazing work, and I haven't personally seen this sort of prompt tuning method used in this way before, and it's just creative in terms of mechanistic interpretability as well, and really curious about what will happen with the further directions section as well. And then on a third place, with $300, we have automated identification of potential feature neurons. So this is from Michelle, and this is a super cool project. And you can see these are some of Neil's comments. They will be quite long for some of the projects, but it's basically great to see that there's this, Neil basically liked a lot of the spirit of automating things and figuring out how we can find new ways to find the potential feature neurons, basically. And then he goes a bunch into depth as well on what sort of the next steps could be and so on. But it's really an interesting work, and attempting to find these, automated identification of potential feature neurons is just always a really, really nice piece of work to go for. So congrats to them. And on a second place with $600, we have identifying a preliminary circuit for predicting gendered pronouns in GPT-2 small. So as Neil also mentioned here, it's one of it seems a bit like a prototypical project that you'd want out of such a weekend as well, because it uses this ACDC, as it's called, the automatic circuit identifier from Conmi, I believe is their name. And it's just super interesting to see that we are able to refine the hyperparameters of these sorts of automatic circuit identifiers in a cool way, and see this in action, which we haven't seen yet. Causal scrubbing has just become a thing, and now we're already trying to automatically find these circuits. So it's really rock and roll to see it happening in the wild. And then there's a bunch of technical details about what are the steps taken within the project, and how can we lead this more towards the pronoun identification task and so on. So overall, really solid work, well executed, and super interesting findings from just a weekend. And it's just super nice to see this sort of work, and hopefully we'll see it expanded in the future. And congratulations to them, of course, Chris Mathwin and Kiyamo Korea. I do not know how to pronounce the last name. And on the first place, we have, with $1,000, we have the wonderful Joseph Miller and Clement Neal, who made the project We Discovered a Neuron, which is not a grammatical error, even though it might look like it. It is simply because they found the neuron for an instead of a, and a bunch of its side semantic related tokens. And this is a very cool project, so it aligns quite a lot with the max activating dataset example finds, and Neil has linked a bit of some extra neurons he's done some visualizations of in the feedback as well, and really cool to see this sort of monosemantic neuron. It's especially the activation patching work that's super cool, and the rest is corroborating, but the activation patching is really good evidence for these sort of hypotheses and the predictions they make. So this is super cool, and it seems like it actually predicts this sort of neuron. It doesn't just activate on an, which is even cooler than just discovering an neuron. So really massive congratulations to them, and super cool to see the transformer library used in this way, wonderful project. So congratulations to them. And then we have the random prize that is given to a random project, and this time this went to distillation by duplication, the importance of layer selection. This is from the Edinburgh team with Roxana Govarek, Paul Martin, and Jonathan Frennert. So $200 in their direction. And now we have project presentations. So we have Ita Iona from the Mental Leap team who will present a bit of their convex set work. And I think we can jump directly to him.
Okay, so I'll just give a brief introduction about what soft prompts are and our first idea, and then how we navigate through several ideas and then our results. Soft prompts or prompt tuning is actually a very simple idea. You take a model, you freeze all its weights, and then you prepend tokens to the input and fine-tune only the tokens embedding. And the idea is to use these tokens to direct the model to fulfill a specific task. So it could be a token, several tokens for summarizations, and other tokens for sentiment analysis, and so on. I won't spend time on this, but it is very useful. It is better than few-shot learning or in-context learning in terms of quality, and it's much cheaper than and faster than doing a full fine-tuning of the model. And then, in the context of mechanistic interpretability, it's also interesting because it directly affects the network functionality, but also lives on the same layer as token embeddings. So it's an interesting place to explore. It could be easily interpretable, but also directly affecting the function, the network's function. Okay, let's ignore that part. Our first idea was based on the concept of speaking prompts. Of one of our team members explored it before. The idea is to take vectors from the model weights and then use them as embeddings and then ask the model to explain these vectors. So explain neuron 2. Neuron 2 will be, for example, mapped to the vector that we are trying to understand. And then hopefully we will be able to ask the model in its own language what things mean. So we wanted to apply this technique over the soft prompts. So explain the task tokens that were learned. Well, it didn't work, but we had a bunch of questions that we had to face. Maybe we don't use the right task, maybe we don't do prompt tuning correctly, maybe we need more or less tokens, maybe we use the wrong model, maybe GPT-2 is too small, maybe speaking prompts is just not useful enough. So the first thing we did was to come up with the simplest task that was useful. So the +1 task is very useful. It takes a single numbers token, and the model then predicts the next number, the consecutive number. And so we managed to find such token. And then we were looking for properties. So maybe concatenating these tokens to have +2, or to multiply the token to have +2, so to gain this compositionality. But it didn't work. We had plenty of ideas about what to do, maybe to explore how much tokens can represent these tasks, how much dimensions are there to represent these tasks. So we have a single token, then we can try and find another orthogonal token that implement the same task, and then others. Eventually, we used the tokens that came up from this analysis and looked for convex combinations. So we can take half of the first token, another half of the second one, and sum them together, and we get a new token that also fulfills the same functionality. And when we found this result, we just extended our study to verify it and see how well it generalized to other tasks, other models, and so on. So this was our research. I will just very briefly go over our notebook. So it's very well organized in my opinion. So we have the installation phase, imports, it's very simple, and then library is where we implement the soft prompt. So we prepend tokens, Then we define our tasks, so we have the +1, +2, and so on. Here we train our model, we evaluate. So we reach 100 accuracy of over the +1 task. Then we store the token and analyze it. Here we load our tokens, we do convex sum, and then we evaluate the convex sum when we reach similar accuracy, so 95% for using these 4 tokens with these convex weights. Here we have organized analysis over other tasks. And that's it. That's what we managed to do during the hackathon.
Awesome work. Really fun to see. And what's like some of the next steps you're thinking about taking with this?
Oh, so there are plenty. So we want to explore it on other models, larger models. We also want. So we had an idea to train the explain task and then use the token of explain over itself to see if we can get something. We want to still study, measure the dimensionality per task. We want to, we had, I don't know, like 15 further directions, so I can't recall all of them at the moment.
Yeah, that was really it was really nice to see how many things you had thought of doing extra. So yeah, really rock and roll. Thank you for presenting that. And I also see we do now have Chris and Clement here as well. I don't know if you want to speak shortly about your work, just like verbally is totally good as well, since you now also were part of the winning teams.
Okay, yeah, sorry. I spoke to Zaki a bit earlier. It's like 6 a.m. my time, and I just woke up to this.
Yeah, that's great.
But I am happy to like share my screen and just go through our report briefly and what we did.
That would be perfect.
So Guillaume and I worked on this identifying preliminary circuits and gender pronouns task. Essentially, this task is so you have a prompt like, so David is a really great friend, isn't he would be the correct response there. So Mark is such a good cook, isn't he would again be the correct response there. We really wanted to understand if GPT-2 small, one of these large transformer models could do this task well, and if it could do it well, how was it implementing potentially a sub-circuit of that task. So essentially our first line of reasoning was to see if GPT-2 small could do this task. We'd use Neil Nander's exploratory analysis tools to just do some prompt inputs and see what sort of tokens it was predicting. And we found that it could do this task very, very well. From there, we move on to this automatic circuit discovery work that Arthur Comney did after his involvement with the interpretability in the wild paper. Essentially, within the methods of this paper or this report, we go through exactly how we use that automatic circuit discovery tool. So you essentially create a data set that captures the behavior. You then label important positions within the structure of the sequence of that prompt. You make a baseline data set. You define a metric to measure the model's performance. On that task, you then choose a threshold value, and that threshold value ended up being quite important. We essentially played around with a few different threshold values, and the specifics of the threshold value can be found in the report, but essentially we found that a threshold value of 0.015 worked well, that it identified a circuit that was essentially about 65% of the performance of the model, but only contained, I think it was about 5% of the model component token pairs. So this was the circuit that we derived with Arthur's automatic circuit discovery tool. It looks like quite a mess here, but it's actually a lot simpler than it looks. Essentially, it breaks down each of the component token pairs and links them via their query key and V compositions, query key and value compositions. And after you've got this sort of preliminary circuit, we found that we were able to group components based on what token they were looking at and where they were doing, what type of composition they were doing. And we also used a lot of Neil's other tools in attention patterns and direct logic attribution to try and understand which of these heads and which of the head token pairs in this big mess of a circuit were most important. And essentially that led us down to, if I skip down here, to this kind of final broad structure of a gendered pronoun circuit that we want to refine further, was this name group, the is group, and the t group. So we found these important heads early in this in the model's layers, this name token component pairs, and they fed through to this is group through the value vectors, and they've transferred information through to the t group through the key vectors. There's still, I guess, in next steps, there's still quite a bit of work to do. We found this like general structure, but we don't actually understand yet how, like what this human interpretable algorithm is. So like how is GPT-2 small fundamentally doing this, and can we explain it? We understand like where information seems to be passing to, but we don't yet understand like what that looks like more precisely. Yeah, I think that's pretty much all I had for my presentation here.
Nice, yeah. It's a pretty rock and roll project. I actually hadn't even seen the ACDC tool before I read your report, so it was quite exciting seeing it as well, just because it's clearly pretty rock and roll. And I'm curious, like, do you have to update your way of looking at the circuits to identify more human interpretable circuits for, you know, now you mentioned this information transfer, and I wonder if you've gotten more information out of it on how to actually interpret it later.
Yeah, so we spent most of the weekend actually using the automatic circuit discovery tool, and less of the weekend in actually interpreting that big subgraph. And so I guess like the next step is essentially just diving deeper into that big subgraph and really understanding why it's passing information via the key vector versus the query vector versus the value vectors, for example. And really actually also even understanding whether our current understanding, whether it's passing from this name group to this is group and then to this apostrophe t group, is that fundamentally like the underlying like baseline circuit, essentially, the underlying information flow, because that was what we speculated based on the contribution of some of the more significant heads, but we didn't confirm that within the weekend. Yeah,
nice. So in reality, it's mostly about actually spending the time looking at it instead of hyperparameter tuning on the circuits identifier. Nice. All right, rock and roll. Thank you for the presentation. And Clemens?
Right. So it all started when we were just like discussing an idea on Friday. And this report in general kind of follows the flow of our discovery and like what we did with it over the weekend. And the idea came first being with the question of how would a transformer know when to use the word and over an a, because that would be usually looking at the token after it because of whether the next word starts with a vowel or not. So the question we had at first was how would a transformer like look into the future and choose n over a. And at first we started with GPT-2 too small, and we realized that actually it's kind of sneaky because it would just always go for the word a over the word n, because our guess is that like if you choose the word a, there's like a million ways to complete the sentence after that, like say like a basket of apples or like a bunch of apples, whereas like with the word n you really only can have like apples. So our guess is that GPT-2 small was small, and that it limited it to only answer a, and we kept trying to make it bigger and bigger, and we stumbled upon GPT-2 large, which with this prompt I climbed up the pear tree and picked a pear. I climbed up the apple tree and picked, it would actually predict an apple with, I think, 3 times more probability than the word A. At first we had just this prompt, and we tried to think of the prompts that would be like, oh, what would make the model predict N, and like every time we'd be like, yes, every morning the chicken laid an egg, right? And it would just be like, no, laid out in the middle of the street or laid its egg in the oven. It was like the model was so good at
Nice.
avoiding the word, which is why we added this first sentence, quite inspired by the interp in the wild paper, and that was successful in making it nudge towards predicting N. And with the EDA notebook, we ran the logic traversals, and we realized that there were actually 2 specific layers that were quite significant in predicting this token N. So the first one is an attention layer, and it mostly looks at the word apple, and this in itself, we're not sure about what happens, because the idea being that in IOI, the task is that they copy a word over from the previous earlier in the sentence in the later sentence, and that's like significantly an attention-based task because it just copies it over. But in this case, because the word and doesn't appear, the sentence earlier is a pair, so the word and doesn't appear. So we were thinking, that's why it needs to go through the MLP layer, because there is no word for the attention layer to copy and get it right. So we found an MLP layer that was significant, and we thought that yes, it's probably more interesting to look at because it's the MLP layer that transforms it into the word N. And when we ran it through, we realized that there was this specific MLP layer that was responsible for the predicted word N, that if we were to ablate out its activation, that the word N would collapse quite significantly. And what we tried to do was this was amazing. We tried to change the activation of every neuron in the MLP layer, and we were just like, well, we don't know whether this will work or not. And because we were worried that like maybe it was like a specific set of neurons, but it turns out no, it was just one single neuron, and we're like, oh, this is quite promising. And we didn't really know what was going on until like we remember like, oh wait, neuroscope is a thing, right? And we went to look at layer 31 and that specific neuron, and the thing was that we were just very confused because for like 20 minutes we were like, oh, this doesn't say a lot, because like how in have black, we were quite confused, like, oh, did we just accidentally stumble upon this graph? And then like half an hour later we realized that, oh wait, no, all of the words after the maximum activating word is the word N, and that was when we realized that yes, this neuron was pretty significant. And one side note is that like because the idea at first was that the choice between the word N and A was primarily a grammatical one, but the fact that the token N could be used as a starting token for the rarer words like anodizing kind of hinted to us that it might not be as simple as like just grammar, because of the tokenization, it kind of blends together with a lot of other things. So, but just to confirm that this was responsible for M, we messed with its activation and its weight, and in summary, it really did bring down the probability of N, and that's how we're sure that this is N neuron. And it's a bit of a pity because we only really started to mess with it on Sunday, and so like there's a lot more to be done. We've discovered this neuron, but there's a lot more questions that we could be doing. One comment on the project was how, for example, maybe you could copy this neuron into smaller models to see whether like this can the function of predicting N could carry over to smaller models. There is this like interesting question that we had at first as well, which is there a mechanism in which this attention head interacts with this MLP specifically? So before, let's say, speaking about how whether we can copy this neuron into a smaller model, we have like, you know, more simple questions of like, let's say we move this from the layer 31st MLP to, let's say, like a neuron in the 32nd layer, does it still work? And for example, if that still works, our guess is that like if we brought it to before layer 26, before that significant attention layer, that like it probably wouldn't work, because in some sense, if you think of attention as like information moving, it probably like moves the information to a correct place for the MLP to interact with this attention layer. So yeah, we pretty much just discovered this end neuron, and I guess there's a lot of things that we can do that will go a very long way after just this one weekend. Yeah, so it was a pretty good weekend overall.
Nice. Yeah, it was a rock and roll project as well. Thank you for presenting. I really loved the exploratory nature of it, right? It's like you're taking a journey into the model and doing a lot of different things to it just to figure out this causal mechanism. So really rock and roll. And do you have personally, like, now you said you began looking at the AND neuron on Sunday. Do you have like some way you would have optimized or changed this process in general towards something from what you were doing into something that would lead you to the results quicker, or?
I think one thing that it was just that because we were looking at the transformer lens library, that actually changing the activations of the neuron was very manual in our code, because the library as of now, I don't think it supports ablation by the layer, but it doesn't support ablation by the neuron. So probably something in the future we could do is that like we could like add that to the library as well to help with the more like MLP based exploration.
Yeah, I can imagine that would be super useful also, because, you know, the plot you have is pretty epic with just like a flat spike. So
Yeah.
that's super fun. Yes. Well, now thank you very much for all the presentations. A few massive thank yous, of course, to the wonderful Neil Nander, who has helped us both with starter resources and with the intro talk, and also this judging here. So amazing that he wanted to help out and he wanted to join again. And you know, the projects make it worth it, as he would say, and as I would say. They are wonderful. And then, of course, to all of the jam site organizers across the world. It was also Lunar New Year, so that coincided a bit on top. But still, all these local jam sites got full and got a lot of people joining, and had an amazing time, it seems. And of course, all you wonderful participants, the people here in the Discord call, and to all of the other people who participated as well. No discrimination here, wonderful people. And to a few others, so Stefan Heimersheim, who also joined the hackathon, he created this, how to create transformer mechanistic interpretability in 40 lines or less. I think maybe it was called 30 lines or less, and then it was updated to 40 lines or less, and now it's 50 lines or less. But really, really wonderful resource, and I'm sure a lot of research participants have, you know, had a say in that, or had a look at that and checked it out. And then to Sabrina Sacken, our community manager, who is rock and roll and helping out with making all of this happen. And to Faisal Bades, who has helped with the judging. And he is also, of course, a part of our Part Lab teams. So a wonderful thank you to them as well, and the people who are like continuing their work with us on their hackathon projects. That's super exciting to see, and some of the projects like approaching some conferences now. So really, really exciting to see. And otherwise, are there any questions from people in the chat? Otherwise, that is basically everything I think I had to say. And I'll stop my streaming of you as well.